Welcome back. Algebra 2, we're in lesson 66, and first we're going to talk about signs of fractions. So for a long time we've been looking at a fraction like this as this is a negative, or it's minus 3 over 4, and a lot of times what we would do is we would say negative 3 over positive 4, and that's not wrong. That allows us to then make that a plus sign. But what we're actually doing when we do that is we are taking this negative 1 that's out front, asking for the opposite of this, and we are multiplying it times the numerator. Okay, so that's what we're doing. So this is actually plus negative 1 times 3/4. Instead of seeing this, what we should be seeing is this. Right? So then that allows us to say that it is plus a negative 3 over 4. Because we always put the negative in the numerator, not the denominator. So we're going to expound on that a little bit more and talk about how there are actually 3 signs in a fraction. So going back to negative 3/4, technically what we have here is a positive 3 and a positive 4 and a negative 1 in front, just like we already discussed. Okay, and in order for it to be a negative 1, in order for it to only affect the numerator, what happens is that we do negative 1 over positive 1 times positive 3 over positive 4, and that ends up being negative 3 over positive 4. Okay, that's how that works. But there is a way for us to change that affects both the numerator and the denominator. There's a reason why we sometimes want to change both of them. So let me give you an example of that. 66.1. I have this problem here, 1 over x minus 3 minus 7a over negative x plus 3. I need this to have the same denominator. How can I make this be the same denominator as this? Well, it's obvious that the components are the same. It's the signs that are different. So we know that if we multiply a fraction, both the numerator and the denominator, by the same value, then we know we can change the fraction and keep the same value. So what I mean by that is we have a negative here, right? So we want to go ahead and adjust our fraction so we can get rid of this negative to start with. So we're going to say 1 over x minus 3 plus negative 1 over 1 times 7a over negative x plus 3. All right, so this becomes 1 over x minus 3 plus negative 7a over negative x plus 3. Okay, that did not change the value of this at all. It just moved our negative sign up to our numerator so that we can see what we are doing a little bit better for the sake of changing our denominator. So now we are going to multiply this fraction by the same number on the top and the same number on the bottom in order to change the sign, and that number is going to be negative 1. So this times negative 1 on the top and negative 1 on the bottom, it's going to change the signs of our fractions and give us a common denominator. But it's not going to change the value, okay? So this will then become 1 over x minus 3 plus negative times a negative is a positive, 7a, and then a negative times a negative is a positive, so that's now positive x, and a positive 3 times a negative 1 is now a negative 3. Now we have the same denominator, okay? Now we can put these together. So that's going to equal 1 plus 7a over x minus 3. And that will be our final answer. All right, so do we see how that works? First, we get rid of the minus sign that is there by multiplying this fraction by what's already there, which is negative 1 over 1. Okay, we change that to the plus, and we get rid of that. Remember how whenever we have a problem, let's say we have 4 minus 2 plus x. Remember when we'd have a problem like that? And I would always tell you, drop your negative 1 in there so you can change the signs. And then that'd be 4 minus 2 minus x, right? Remember that? The imaginary 1 or the invisible 1 that has to live here so that this gets changed. That's what you're doing. This is what that is. You're dropping that negative 1 over 1 because we have to make it a fraction. And we know that any whole number over 1 is still a whole number, right? So we're not changing the value of this by making it a fraction. It still remains a negative 1. We're just making it a fraction so that we can multiply the top and the bottom appropriately and carry that value over. So it's the same concept as what we used to do right here. We're just applying it to a numerator and a denominator at the same time. All right, and then getting rid of this minus sign simplifies our problem to the point that we can see now when we multiply by negative 1 by the same number on the top and the bottom. If we'd had a negative sign here, then it would be hard to see that. So that's what we're doing. We're simplifying it first by multiplying this, and then we're changing to find the common denominator by multiplying both the top and the bottom by the same number. All right, so let's do 66.2 and expound on that just a little bit more. So in this one, we have 4x plus 5 over x minus 3 plus 2x minus 3 over 3 minus x. Okay, so first of all, that's a little bit difficult to see exactly what the signs are. So I'm going to put them in the right order. I'm going to rewrite it as 4x plus 5 over x minus 3 plus 2x minus 3. All that's the same. Now I'm just going to rearrange this to match this. But the negative sign has to stay with the x. So negative x, and this is a positive 3 plus 3. Okay, so I just rearranged it. Now I can see that I need to multiply this by a negative 1. But if I multiply this by a negative 1, I have to multiply this by a negative 1 to keep it the same value of a fraction. So negative 1 over negative 1, and then we multiply. This remains the same. This becomes negative 2x plus 3 over positive x minus 3, right? Negative, positive becomes negative, negative becomes positive, negative becomes positive, positive becomes negative. Okay? Easy peasy. You guys can do this. And now, because we have the same denominator, we can put them together. So we have 4x, and we have a minus 2x. So it's minus 2x plus 5 plus 3 all over x minus 3, which allows us to combine these. So it's 2x plus 8 over x minus 3. Okay? So do we see how we were able to combine the like terms by doing that? That made it so much easier, right? And that would be our answer for that. Okay, let's talk about triangles. First of all, we're going to talk about 30, 60, 90 triangle. So we see 90 right away. We know what? This is a right triangle because 90 is the right angle. So we have a triangle that looks like this. This is going to be your typical 30, 60, 90. So this is 90. This one is 60 because it's the bigger of the 2, and this one has to be 30, right? So 60 and 30 is 90, and 90 is 180. We know that that is what the internal degree of a triangle is. So let's look at the sides. We have 1, we have 2, and we have the square root of 3. And that is always similar. The degree of measure is always going to be similar to this. Right triangles whose acute angles are 30 and 60 are encountered often in physics and engineering. And they're called 30, 60, 90 triangles. These triangles are all similar to this one. Okay, they all have that same type of scale. Sometimes we forget the lengths of the sides of this triangle and forget which length goes where. If we can remember to begin with an equilateral triangle, and an equilateral triangle is just, oops, my pen messed up. Sorry. Sometimes when I draw backwards, like with a triangle, it does that. Let me try again. Equilateral triangle is one where all the sides are all the same. So this is 60. Oh, let me get my pen back. So this is 60, this is 60, and this is 60. So we start with that, and we give them all the same length right here, right? Next, on the left, we draw the perpendicular bisector right here. We cut the equilateral triangle in half. Right, let me put this right where it's supposed to go, right in the middle. All right, so now it's bisected. Doesn't that look like that? It does. So that reminds us that it's bisected, so 60 divided by 2 is going to be 30. Scratch that out. It's going to be 30 and 30, right? That's divided in half. It's still 60, but it's divided in half. So 60, 30, and this becomes 90 down here. Now, because this is 2 across the bottom, it gets divided in half. 2 divided by 1, or 2 divided by 2 is 1. So 2 and 1, right? And if we use Pythagorean's theorem, right, and we say, we know that a squared plus b squared is equal to c squared, which is the hypotenuse. I've gotten to where I like to, instead of say c squared, I like to say h squared, because that reminds me, you know, of what this is, the hypotenuse. And the hypotenuse here is 2, because it's the one that's directly across from the 90 degree angle. And one of the sides is 1. So 1 squared plus b squared is equal to 2 squared, right? So this is going to be 1 plus b squared is equal to 4. So we subtract 1 from both sides. B squared is equal to 3. So when we unsquare b is equal to the square root of 3. And that becomes that height right there. So that is how we get back to the 30, 60, 90 lengths. 1, 2, and the square root of 3. All right, so let's try one. I'm going to just erase this bit here. And if you want to, you can rewind and make all those notes. But we're going to use similar triangles to find x and y. And I am going to erase the dimensions here. This is y, this is x, and this is 5. Okay, so we know the similar triangle is going to be this, right? I can't draw it very well because, well, I'm not the best artist in the world. That's a little bit closer to what we want. So we know this is 2, this is 1, and this is the square root of 3. This is something that's going to help you on the ACT as well. You're going to be given similar triangles at some point, and if you memorize the 30, 60, 90 similar triangle scale, then you will be able to find the measures that are missing on a 30, 60, 90 triangle. Okay, so we know in this similar triangle that 2 and 5 are our relative numbers, right? That's our scale factor. So 2 times some number is equal to 5, and that's our scale factor. 2 times some scale factor is equal to 5, so the scale factor is 5 over 2 because we divide both sides by 2, and that leaves a fraction, 5 over 2. That's our scale factor for all of them. So now we can find y, and we can say 1 times our scale factor. Remember, we said 2 times our scale factor gave us 5. So 1 times our scale factor is going to give us y. So 1 times our scale factor of 5 over 2 is going to give us 5 over 2. So that is going to equal y. Okay? Now we can do the same thing for x, right? We know that we have a square root of 3 here times our scale factor, that's going to be x. So the square root of 3 times our scale factor of 5 over 2 is equal to, how do they do that? 5 times the square root of 3, because we put that over 1, over 2, and that's equal to x. So that would be 5 times the square root of 3 over 2, and this one would be 5 over 2. Easy peasy. All right, if you have any questions about scale factor, feel free to ask. Another way that you could do that is by simply putting the ratios together. So you would have 5 big over little, 5 over 2, okay, and 5 is, let's do x. 5 corresponds to x. They're on the same triangle. So you would put x here, and the corresponding side to x would be the square root of 3. So then you would just cross multiply, and you would say 5 times the square root of 3 is equal to 2x. Well, then you just divide, right? So this is going to be equal to 5 times the square root of 3 over 2 equals x, which is the same thing we got here by using the scale factor. So it just depends whichever way you want to do it, you're going to end up with the same answer. All right, this is the proportion method. This is the scale factor method. The proportion method honestly is a little bit faster. There's fewer steps that you have to go through. It's all up to you as to which way you want to do it. All right, and that's all we have for lesson 66, and I will see you in lesson 67.